everyone. First of all, once again, a very hearty welcome to all of you on this second session of technology interventions to manage current challenges. At the outset, I also would like to thank Chemtech Word for giving us this opportunity, and we are really honored by that. In yesterday's session, for those who attended, we got a lot of insight into technological solutions to convert refineries into petrochemical hubs and increase the production of specialty chemicals, which is the need of the day, which provides swing capacity between fuels and refineries and petrochemical refinery products and the petrochemical. We also got some insight into the bottoms of the barrel technologies. Yesterday, we also heard a number of prominent speakers talking about the India growth story. And all of them were quite optimistic that growth of petroleum, petrochemicals in India is going to continue for next 15 to 20 years minimum. And there is going to be increasing demand of energy for these periods. I fully share their optimism, and I also firmly believe in that. But the current dilemma with the industries are many. First is how to meet this growing demand of energy, at the same time reducing the emissions, which is the need of the day. How can we reduce our emissions so that the development and the environment can coexist? And also the current situation of tremendous pressures on the margins. While doing all this, how do we retain our margins? And one thing on which all refineries and petrochemicals have been focusing to achieve all these three objectives has been the focus on increasing efficiency and reliability. So today's focus on this session is also on reliability and efficiency. We have papers from Mr. Derrick Bauer, who will talk about improving the reliability of machines in corrosive environment. We also have a paper on by Mr. Pramod Dalvi on providing standardized, customized solutions to increase efficiency as well as reliability through EFDs. Of late, there is a lot of talk about green hydrogen. The interest in green hydrogen has been number of concurrent technological developments are taking place, which is increasing the interest on hydrogen. And it is being slated as fuel of the future. Some of these developments are increasing demand of hydrogen in the industry itself, very rapid developments in the renewable energy, which along with it brings the technological problem of the fluctuating natures, the seasonal natures of these energies, and the requirement of a sink for these fluctuating energy sources. Also, there have been tremendous developments in the field of electrolyzers, and also very aggressive targets taken by the governments worldwide and the industries to decarbonize their economies. All these factors are together leading towards hydrogen as a very interesting fuel for the future. All of us, we have seen the kind of revolution which is taking place in the renewable energies. And this has been made possible because of long-term policy support by the government, several fiscal incentives, and also industry and the government coming together to achieve a common goal. A similar kind of policy incentive has been, policy initiative has been taken by government in the form of National Hydrogen Mission, which will come into effect in next fiscal. And about 1,500 crores have also been allocated for National Hydrogen Mission and the renewable energy. So we also have a paper on hydrogen production, storage, liquefaction by Mr. Harwood on this. So before I invite Mr. Harwood, Matthew Harwood, I will request my fellow panelist, Mr. Bhaskar Pukan, who is Director Refineries, Numaligarh Refineries Limited, to also share his thoughts on how to meet the current challenges through technological interventions. Thank you.
Thank you, Mr. Bhandari, and thank you to the organizers for having invited me. Bhandari has already covered most of the issues that borders the refining sector or opportunities that is ahead for the refining sector. Going forward, we have to fight a three-pronged battle. When the margins are low, we have to bring in investment to be petrochemical or chemical ready, because margins are low. You want to increase the top line while decreasing the production cost. So when we talk about reducing the production cost, you look towards optimization, reduction of energy use, increase of reliability. So one leads to the other. While you have a pressure on the margin, you need to increase the top line by going for more value-added product, perhaps low volume at times. But also you have to look at the cost reduction all the time. In India, we had a long-running benefit of labor being cheaper than the other developed countries. Gradually, that advantage is getting eroded. For successive decades, India has seen a phenomenal increase in the wages, mostly for the lower rung and bottom of the ladder kind of people that we engage in the industry. So this is a challenge going forward. So people are actively looking forward for optimizing the manpower cost. By resorting to very aggressive automation. So whenever we talk about new plants coming, we are looking aggressively towards automation. So once we look towards automation and digital intervention, refineries are getting more and more digital. So time is not far when actually we will see IT engineers manning shift along with the chemical counterparts who are responsible for running the plant. Of course, some maintenance guy will always be there. So this is the way forward, I think. One, chemical; second, cost reduction; third, trying to find more and more smart ways of doing refining. So with this, I give my I'll hand over back to Mr. Bhandari to take the session forward.
Very interesting observation, Mr. Fukan. IT engineers manning the operations along with chemical engineers. So I think this possibility, I think in near future, is appearing to be a real possibility. So Mr. Matthew Harwood, may I request you to go ahead with the presentation on hydrogen production, storage, liquefaction.
Yes, good morning from the UK, and good afternoon to all of you in India. Very nice to be here, and thank you very much for the invitation and the initial words there from both of you. I speak from England today with some nervousness, mainly nervous about the cricket, which is going on at the moment in India, where England are in a very perilous state at the moment in terms of our performance on the cricket pitch. But I would like to just give you a little bit of an oversight of our business, McDermott, what we're doing globally and also in India, and then just say a few words about our approach to the hydrogen market opportunity, which we see as a great opportunity, but there are some risks and some challenges in that market opportunity, which I'd like to share with you too. I'm just going to share some slides with you guys on the screen. I hope this works. Perhaps I can get a thumbs up from the organizer if this is coming through clearly. Let's go on to presentation mode here. So yeah, I want to talk about hydrogen production, storage, and liquefaction opportunities and challenges. but first, a couple of words on McDermott. This slide shows an overview of McDermott's capabilities as an engineering and EPC contractor, where we deliver projects onshore and offshore, and really throughout the energy value chain, right from the upstream right down into the downstream, and increasingly active in what you might call energy transition technologies. We are global, but we do have a long history and a big organization in India. So we have more than 2,000 employees across a number of offices in India, currently delivering work of around, in total, $2 billion worth of EPC projects, actually offshore projects at the moment. But we have a long history of working in the downstream in refining and petrochemicals, often with our strategic partner Lummus, who are also participating in this conference. And we work very closely with Lummus around their process technology into refining and also into petrochemical complexes. We have a strong focus as an EPC contractor on the whole energy transition and sustainability issues. We have 4 sustainability goals within our company. Firstly, to develop sustainable solutions for our clients to support them in their energy transition. Secondly, to contribute to sustainable economic growth wherever we work internationally. Thirdly, to reduce our own operational environmental footprint. And we have a strong focus on scope 1 and 2 greenhouse gas emissions at the moment, looking to deliver net zero by 2050 and a 50% reduction by 2030. And we also finally look to promote well-being in our communities, both internally and externally within McDermott. So within the energy transition, we're focusing on 3 broad areas: delivering projects with lower embedded carbon in them and low operational carbon. We're calling it low carbon delivery or net zero projects. Delivering new technologies, and hydrogen falls into that category, the second category, and increasingly looking at opportunities in the circular economy, especially around waste and plastic recycling opportunities. Moving to hydrogen, we see a very strong potential growth in hydrogen, the hydrogen market. The chart on the left is from the World Hydrogen Council, of which we're a member, showing potentially tenfold growth in the volumes of hydrogen production and demand globally between 2020 and 2050. And you'll see on the right hand side a similar analysis for India, where you see a similar potential strong growth in demand for hydrogen, which we see as a very exciting opportunity for India and for the energy value chain in India. If we look have a look at the overview of the whole hydrogen value chain here, and what we've tried to do here is lay out the entire chain and look right from the sources, the original source of the energy, through to the hydrogen vector, the energy vector, and then through to the uses of the hydrogen downstream. It's obviously quite a complicated picture, but it's a picture which affords a lot of optionality as well. I think the great thing about hydrogen is that it's a clean energy carrier, which can be used to transfer either electrical or chemical energy into a vector, which can be used in many different applications downstream, whether it's transportation or heating or into industry. And we as a company are particularly focusing on its production. So the left-hand side of this chart, production through electrolysis, or its production through reforming, particularly methane reforming, either via SMR or ATR in order to produce hydrogen. We're also very focused on the next potential steps of the chain, the transportation, storage, and doing a lot of work to look at how do you store the hydrogen in an efficient way, and how do you transport it. And we're very active with work around liquefaction of hydrogen and also cryogenic storage of hydrogen as well. Just a page with some of our hydrogen credentials and experiences. A lot of experience in steam methane reforming to produce hydrogen. There's a picture of one of the plants there at the bottom. On the right hand, the picture on the right hand side at the bottom is a tank that we're currently constructing for NASA, the largest cryogenic storage tank for hydrogen, which is 5,000 cubic meters in volume. But hydrogen storage is going to be one of the issues that we will need to crack in order to develop hydrogen at scale, particularly if it is generated through green hydrogen and, as was discussed earlier, through intermittent renewable generation. We'll need to have good storage for hydrogen if the market evolves in the future. So just to kind of round up then, to talk about the opportunities and challenges for the hydrogen market as I see them. I think on the opportunity side, clearly hydrogen affords a route to the decarbonisation of many sectors which have been difficult to decarbonise. While some economies have made good progress on decarbonising the power sector, it's been sometimes more challenging to decarbonize sectors such as transportation, where hydrogen can play a strong role, certainly in heavy duty transport, potentially in light duty transport as well. Clearly heating, maybe not so much of an issue for India, but clearly for Northern Europe, we use a lot of gas in heating, and it's quite difficult to see how to decarbonize that. And hydrogen is certainly a very interesting prospective fuel for decarbonization of essentially urban and residential heating. And then I think into industry, clearly for this audience, refineries use a lot of hydrogen, and there are ways in which we can look to decarbonize the hydrogen that's used in refineries, but also very interesting opportunities within the steel industry and within the fertilizer industry as well. I think the other benefit of hydrogen really clearly is it's a clean transportation fuel. So not only can it decarbonize one's activities, but it also can reduce air pollution, local air pollution within cities, which I think is another benefit of moving to hydrogen as a fuel, certainly within the urban environment in the transportation sector. I think its ability to act as an energy store can really support the development of renewable power, particularly intermittent power like solar and wind, where you have this challenge of intermittency, and in some cases it can also allow for new renewables to be built without upgrading the transmission grid, and because you're actually using excess renewable generation and converting it into hydrogen. I think it's also exciting that it can, for nations that are very dependent on energy imports, it's another way for them to continue to develop energy independence. And of course, we believe that it's a new industry that will support economic activity and job creation as well. And clearly on the challenges side for hydrogen, I think the cost is still very high, particularly for green hydrogen, and we need to do work to bring down the cost of the technology, bring down the cost of certainly the capex cost of the projects, but also to scale up, particularly in green hydrogen with the electrolyzers, to scale the projects up radically so they can actually start to benefit from economies of scale. And we need to do more work on customer acceptability. And also that goes hand in hand with health and safety as well, of course, to prove that we can use hydrogen in these different applications safely. And there's a lot of focus on that within the World Hydrogen Council at the moment. I think, practically speaking, as I mentioned, hydrogen storage at scale will be a real issue, and actually will probably go beyond surface storage if it takes off. And we'll need to look at subterranean storage for hydrogen to be able to have the storage capacity needed. And then finally, I think this is the point that I'll end on. Clearly, this is a technology which is still growing. It's nascent, and across the world, we'll need to see mechanisms to support the scale up and the application of hydrogen as a technology in its different settings through appropriate regulatory support and incentives until it can stand on its own 2 feet relative to other potential fuels. So I will pause there and hand back to the organizer, and happy to take questions now or later, as according to how you want to move forward.
Maviz, you would like to take questions now, or?
The questions we can take at the end, sir.
Okay.
Because there will be so many presentations, so maybe some of the questions will get answered during the course of the presentations or during the discussion. So we can take all the questions in the end. So whatever has not been answered, we can answer.
Right.
Okay, thank you.
Thank you, Mr. Harwood. I hope the cost of hydrogen comes down in the near future, so that it becomes a choice of the fuel of the people and also the industry. So now we have the next presentation by Mr. Pramod Dalvi. Mr. Dalvi is the key accounts manager of Danfoss, and I invite Mr. Pramod Dalvi to go ahead with his presentation.
Good evening, sir. And to introduce, I am Pramod Dalvi. I take care of oil, gas, and chemical segment in Danfoss for business development part. And today, we from Danfoss end, we will be presenting AC drives, which is used for energy savings and other process, for parameters, how they are reliable and energy efficient. Am I audible?
You're audible, but there's a lot of light falling on your face, so we're not able to see your face clearly. Okay. Yes. Yeah, this is better. Yeah, slightly. That's perfect.
Yeah.
And also, if you can increase the volume, please.
Yeah, please.
Sure. Okay. So I will share my screen presentation, sir.
Mr. Dalvi, if you can adjust your camera, because the camera is tilted now.
Yeah.
Okay,
sorry.
now we can see.
Now it's right. Sorry, I think there is some challenge in my laptop on the camera, so I am working on iPhone as well.
No worries.
So you are able to see the screen, right? No?
Yes, sir.
Okay. So we are Danfoss is a family-owned business, and they have started way back in 1933. We have 87 years of long strong growth, and we are market leaders in core industries. This is Danfoss corporate headquarters at Denmark. We are operating in 4 segments. Again, we name it as Danfoss Power Solutions, Cooling, Heating, and Drives. And the business percentage in terms of revenue, it is exactly in the order of 35, 27, and 23%, and 15%. So we belong to Danfoss Drives, and we have a share of 23% in our group. We hold a market 2 position. Danfoss works in core and clear strategy, where we are either one or 2 in the market position. So here we are market number 2, both globally as well as in India. We have close to 5,000 employees now, and we have 10 factories in 7 countries, and around 1.5 billion euro annual sales for our Danfoss Drives division. As we have mentioned, we have 10 factories. So these factories are globally there in mother factories in Denmark, and then we have another factory in Finland. Danfoss has acquired this Vecon brand in 2014, and globally we merged as a one top company.
Welcome back to Refining and Petrochemicals World IE 2021. Really sorry for the small technical glitch. I now hand over to Mr. Pramod Dalvi, Key Account Management, Danfoss Industries, for his presentation. Over to you, Pramod.
Yeah, good evening, sir, and sorry from our end just for some technical issues. Danfoss is a Denmark-based company established in 1933, and we have a strong 87 years of strong growth, and we are market leaders in core businesses. This is the picture of Danfoss headquarters in Denmark. We are operating in 4 major segments: Danfoss Power Solutions, Cooling, Drives, and Heatings. And we belong to Drives division, which we're having more than 23% of share in group, and more than 5,000 employees, 10 factories in 7 countries, and more than 1.5 billion euros sales is done through Danfoss Drives. We are working on a core and clear strategy, where we are either 1 or 2 in the market segment. In Danfoss Drives, we are market 2 position. We have 10 factories, as I said in an earlier slide, and those 10 factories are in Denmark, Finland, Germany, 2 factories in China. Then we have 3 factories in USA, and most important is we have a factory in Chennai, India, which was inaugurated in 2014. And with all 4 divisions in Danfoss under one roof. I'll show you this is a real picture of Danfoss India Orgadam factory. It is 40 kilometers from Chennai outskirts, and this is 1 kilometer long campus and 50-acre land. And those days we have invested around 500 crore in building this campus. The key communication on this campus is this is energy efficient campus, and we have our own 1.12 megawatt solar power plant, which 90% of this campus demand is supplied through solar energy. And this is the first LEED Platinum campus in India. Like car parking has a solar panel on the roof, providing the shed as well as the generating electricity. More than 1,000 employees we have in Danfoss India, and then you can see the spread is across each region in within the India, and we are also operating through wholesalers and resellers, and we have 10 warehouses in India. We have both white collar, blue collar strength for this operations. So coming back to the real discussion on the case stories part, as suggested by panelists, we have picked up 2 case stories, one in petrochemicals and another in refineries. The first one which we are presenting is for Kochi Refinery for the PDP PP where we have supplied an active front-end VFD for sub-X incinerator fan application. And this project has been delivered in 19 and it was successfully commissioned in 2020. The key challenges about this project is definitely the environment, where you see the moisture dust and the salt mist. And then since the ratings are very high, like 550 kilowatt and in that range, we have very high harmonics, which is input harmonics, which will cause high transformer and cable duration, which will always cost more when in capex. So this is one very big issue when you are operating with VFD and a higher kilowatt motor is the input high current harmonics. And then because of this high harmonic reactive current, your power factor also becomes low. And due to all these 2 major reasons, your efficiency comes down. And then third major issue, which in refineries you will see, is the distance between motor and VFD is high compared to other industries because the motor is situated in the sometimes hazardous area. So in this case, there was a distance of around 400 meters, and since this is a high rating motor, there was 3 runs of cable. So effective length was around 1.5 kilometer. And what happens due to long distance, there is a voltage drop across the cable, and this when the motor sees the voltage, it is a less voltage, hence the current goes up, and there is a temperature rise in the motor, which is totally unaccepted in this segment. So these are the challenges, and Danfoss came up with the discussion with various consultant and customer and the Linde, who is a process licenser, that we will offer a solution with an active front-end configuration. So what benefits we got, doing this active front-end is we first is definitely Danfoss has provided the coated PCBs to take care of harsh environment. I will tell you in subsequent slides. And then we have our own solution for the long distance cable is our LR filter, which is giving less dV by dt and the less voltage drop. So those are the key things we have implemented. And this active front-end configuration has enabled us to give the low current harmonics below 5%. So 35 to 40% if we would have used the standard 612. Now with this solution, it has gone below 5%. So definitely the transformer and cable duration has been decreased. The power factor has been improved to 0.99. So else otherwise it would have been at in the range of 0.84 or 0.85. So for a 550 kilowatt motor, this is very, very low, and there is a loss of definitely an energy in efficiency on the part. And then the most important thing is with this active front-end solution, we have a voltage boost facility, and we stand out in the market that we can boost the voltage up to 30%, which is programmable depending upon the application, the length. We can program up to 30%. This will compensate the voltage drop across the cable. The motor will see the exact nameplate rated voltage, and there are no issues of lesser voltage and higher current and temperature rise. So this is one of the major advantage for high power drive active front-end drives can give. And third very important point is when the input voltage is fluctuating or in imbalance. In that case, the active front-end drives will ensure a steady state DC voltage, so your system is also stable. So these are the key benefits what active front-end solution and LR filter will give. I will just run through what it is mean by harsh environment. So this is on the the PCBs which are used in Danfoss drives are 3C3 coated. This is in compliance to IEC 60721-3-3, where it protects against the environment pollution, aggressive gases, and moisture and dust. You can see in the red, for example, if it is used, that the differences in 3C2 coating and 3C3 coating, it is almost 10 times. So Danfoss drives are having a built-in feature of having 3C3 coating, and because of this, there is a high, increased lifetime, reduced maintenance, and then you will see reliable operation in harsh environment. This is a configuration where the active front-end drives comes in. So there we have three major components: the filter, and active rectifier, and inverter. So both active filter, active rectifier, and inverter are both IGBT based. And if it is a normal 6-pulse drive, then this active rectifier is either diode based or a diode plus thyristor based. In Danfoss drives, we have this modular construction, so where the active front end and the inverter both are the same unit. So a user has an advantage that you can always keep only one unit as a spare. Otherwise, the spare cost will also go up. So it is programmable. That same unit can be programmed as an inverter, and or it can be programmed as a converter. And it's a free software. Danfoss has no charge to do this. It's not a licensed software to do convert inverter into converter. This same active front end can be also put it in a modular construction where it can be programmed for redundancy. So in case of failure of one unit, other unit can work without any stoppages. And this is the key point which we were discussing before on the voltage drop. So why how active front-end solutions stand out? There are three solutions where we can always put an auto transformer as an input to boost the voltage, or we can put in PWM transformer at drive output to boost the voltage. And third is what active front end, what we have used in this case story. So what are the limitations on other two is you can always boost up only up to 10%, whereas in AFE you can go up to 30%. And then for other both the solution, you additionally passive filter is required. And if you give that, then your efficiency goes down. But with the active front end, you can still maintain the efficiency at 95 to 97% and still also have the harmonics below 5%. And if your application is regenerative, in this case it wasn't, but then it has an additional benefit that you get the regeneration also. There is a low impact on other solutions, but then there is a high impact on the efficiency side, and the price impact on active front end is medium, you can say. So next case story, I will talk about the refineries. This is a project Danfoss has done and at MRPL for the desalination plant 30 MLD, where we have supplied a lineup, and the customer the application is high pressure pump, and there was a drives supplied almost 4 megawatt load. And here also, because since it's a 4 megawatt load, the high current harmonics is a major issue. And the second major challenge what has been observed in is the uptime, because these are very critical application, all are working. There is no standby. So if one fails, then the complete pump is down and it will impact the production. So customer has to keep the high spare. So what Danfoss has done is we have offered a common AC lineup, C-shaped lineup with a true 12 pulse module and definitely a coated PCBs as a default in this segment we offer. So low harmonics because compared to AFE gives 5%, but this solution gives below 12%. But still you are meeting IEEE at the primary of the transformer. Then drive sync has what the feature which I will explain in next slide is this ensures the system redundancy, and if your application is critical, this is very, very helpful. Then what Danfoss has done is we have done all this lineup in one frame of the module, so that the end user will can keep the lower spares. So we have done the modular construction. It will come in subsequent slide. So all the low power kilowatt, like 110 kilowatt and 150 kilowatt and 180 kilowatt, were built in the 12 pulse customized engineering. So you can no need for having additional filters for the low rating drives. So this is the configuration, how it looks like when you go on the common AC 12 pulse configuration. So you will have a 2 transformer and 1 bus coupler. So in case of one transformer fails, bus coupler can take it, share it to the other. So transformer redundancy is also ensured. And then if you see, there are 2 inputs going to drive. So one star and delta. And the red one, if you're seeing that 1100 kilowatt rating is very important critical application, which is built in on the drive sync feature. So Danfoss drives has a true 12 pulse design. That means our drives is having star and delta configuration 2 diode bridge as a built-in, and where our competitions give 2 different drives and make a 12 pulse design, but this will have an effect in if both the loads are different, and there can be a circulating current flowing through transformer. So built-in 12 pulse converter is called true 12 pulse in terminology when it comes to industry. So it's a factory built module. It is a one box, one black box for a customer, and then definitely on the customer values it gives below 12%, and there is no imbalance between the star and delta winding, that as we have said, and then definitely the less inventory. This is what is one of the key features of Danfoss drives. We can build it on the modular construction, and for 1 megawatt motor, we have engineered 4 modules of 250 kilowatt module. So in case one module fails, the applications run on 3 modules without any interruption, and then you can remove the module and then always you can repair it or replace it offline, also online, or both the engineering can be done. So this is very popular in high power ratings in various industries, in cement and metal, and in oil refinery and chemicals also this is picking up. Alternately, I think this is not done in this case story, but this is another feature in Danfoss premium drives, that we can also do the hot standby configuration. So in this case, one inverter is running on load and second one is on standby operation. Both are working, and both the waveforms are getting checked for the healthiness. And in case one drive fails, then automatically within 20 to 40 milliseconds, the other bumpless changeover can be taken. So for very critical applications, we have seen even in process fan, ID fans, refinery and chemical industry is opting for standby drives. We are working with a lot of end users on requirements of this. So this can be also one solution which some of the contractors or consultants and end users are working in this segment. This is a real picture of our factory in Chennai, where we do have complete engineering and full load testing. These are the four major test labs in Danfoss. You will see first one is the power electronics lab, where we can test the more loads up to 800 kilowatt, and now it has been enhanced to 1.2 megawatt. So both 12 pulse and active front end up to 1200 kilowatt motors can be tested for the full load temperature rise in Danfoss factory. This is one of the key benefit to in this segment. So we can definitely simulate everything at our factory, so that it goes to site and we don't spend more time in commissioning. The EMC is another challenge in high powered rise, and when it comes to various industries. So we have a EMC test lab. This can be done, EMC compliance can be done in Danfoss, Chennai. We have an IP panel test setup in Danfoss, where we can, it's an environment chamber where we can test up to minus 25 degree and plus 70 degree can be simulated in our factory. And definitely we have all the major certifications of BV and UL and so this is all about presentation and if I think we will wait for questions now or maybe towards the end. So this is from Danfoss side, ma'am and sir.
We will take all the questions at the end.
Yeah.
Because we have one more presentation now coming from Mr. Derrick Bauer.
Yeah.
And after that, we will take the questions.
Okay. Okay. Yeah. Thank you.
Yeah. Thank you, Mr. Dalvi.
Yeah.
Very clean, robust, cost economic solutions provided to both the places. And now with the growing focus on energy efficiency, I think more and more VFDs are being required by the industry. So probably you'll be in a better position to provide good solutions to them.
Yes, sir.
So maybe invite Mr. Derrick Bauer, please.
Oh, thank you. Are you able to hear me okay?
Yes.
Yes.
Okay, great. Thank you. Appreciate the opportunity to speak at the Chemtech World IE. And I'd like to make a presentation on specialty coating for hydrogen recycle compressors. This is very commonly seen in the in refinery compressors, compressors in refinery application, also in petrochemical industry as well. Hydrotreating in just to give a simplified background of what it involves, basically hydrogen is introduced to a feed gas stream and it reacts with the impurities that are in that stream, specifically nitrogen, oxygen, sulfur, chlorides. Then as the process gas goes through this, it goes through separators to remove the hydrogen and these impurities. Through a scrubber or an absorber is supposed to take those impurities out. Then it goes back through a hydrogen recycle compressor and it is fed back into the process. The scrubbers do not always pull out all of the impurities, and these impurities do get carried over into the hydrogen recycle compressor. Oh, sorry, I went the wrong way on my slide. One of the major impurities that we see in the centrifugal compressors is ammonium chloride. And this is a reaction of hydrochloric acid and ammonia. And this is a very potent reaction. It occurs very readily. Shown in the picture examples here are actually just a jar of ammonium chloride and or hydrochloric acid and ammonia. And even the vapors just coming off the bottle begin to react and form ammonium chloride. And it's a highly corrosive salt, basically, that deposits more prevalent on the inlet stages of a hydrogen recycle compressor. This is showing some of the buildup and the heavy fouling that occurred on the inlet end wall of a compressor. This is showing a compressor diaphragm, which is fouled with the ammonium chloride deposits. And here we see the heavy deposits on the first two impeller stages of a centrifugal compressor. One of the major issues is this foulant builds up and it closes up the flow path of the impeller, not allowing the process gas to come through as the design intended. This could lead to lower efficiency and in severe cases, even higher vibration that could lead to a premature shutdown. In the case shown here, the deposit ended up causing corrosion pitting on the surface of the impeller. The impeller was 17.4 pH stainless steel, which has very good corrosion resistance in many environments. However, after cleaning off the ammonium chloride deposits, you can see the pitting of the surface of the impeller. And pitting corrosion is a very dangerous form of corrosion in any sort of rotating equipment. Shown on the left is a photomicrograph. It's a cross-section of a corrosion pit, where what you see on the surface is a little round dot, but underneath of that and going into the material is a very sharp crack. It is especially chloride corrosion pitting, where it goes along grain boundaries of the material and makes a very sharp, atomically sharp crack, really, and this creates a very high localized stress intensity. The graph on the right is showing the fatigue endurance limit of materials, and rotating equipment is under cyclic loads with each revolution, and you can see that the fatigue endurance limit on a corroded surface with corrosion pits can be 4 to 5 times lower than the expected endurance limit in just in standard air environment. So this has a potential to significantly reduce the life of hydrogen recycle compressor and cause premature shutdowns. So one possible solution is the application of a coating, which is really just the layering one substance over on top of another. And the purpose of that is to create a composite system that has better properties than either material by itself. This example is just showing elephants covering themselves in mud to protect themselves from the sun. Within the centrifugal compressor industry, one of the most standard or commonly available coatings, I call it an industry standard just because that is really what it has evolved into, is really just a non-stick coating. It has a corrosion resistant undercoat. It's just basically a ceramic undercoat, and then the top coat is really just a PTFE, or commonly referred to as a Teflon top coat. Really no different than the Teflon top coats that are on cookware. This technology has been utilized for at least 30 to 40 years, and it's been very commonly used in centrifugal compressors in all applications, not just refinery and petrochemical. There are many modifications of it. Each company and other third-party coating suppliers have their own variations. They are basically all the same. There's a corrosion-resistant undercoat, and there is a non-stick top coat that is placed over top of it. One modification shown here that is utilized by Elliot Company is the top coat utilizes fluorinated ethylene propylene, which is just a different type of Teflon. It's a derivative of it, used for its increased non-stick properties and slightly higher durability. Another coating used more commonly in petrochemical industry and to some extent refineries is an Electroless nickel coating. This is basically a nickel phosphorus alloy that is placed over top of on the surface. It's called Electroless because this is applied by a submersion process where no electricity is needed to kickstart the reaction. This applies a hard, durable coating that will withstand operations and last for a 5 to 7 year turnaround. And it is corrosion resistant in many applications. So in looking for possible solutions specifically in hydrogen recycled compressors, another option that has been used for the compressor and centrifugal compressor industries in general is liquid injections. Naphtha or some other sort of petroleum-based product is sometimes used to clean the compressor. It works very well in hydrocarbon type of applications. However, for ammonium chlorides, it is not very soluble in naphtha. So it can knock some of the buildup off the surface, but it is not really doing an effective job. Water could also be used. Water injections, they're used sometimes to keep the process temperature down, but they could be used for cleaning as well. And ammonium chloride is very soluble in water. However, the biggest problem with water is that it can actually accelerate the corrosion process. And that is certainly not something that is very beneficial. So, and thirdly, if a unit has been installed without liquid injection capabilities, there is a heavy amount of rework and in order to put in the nozzles to apply the liquid injection at each stage of the compressor. Coatings are another solution that has been implemented. These can be used after a centrifugal compressor has been installed with minimal impact on the shutdown time. It will not affect the process, less capital cost in order to put it in. Mention the currently available coatings. There's an organic top coat coating or a Teflon or derivative of that, or Electroless nickel. Within the centrifugal compressor industry, all the fouling resistant coatings have focused solely on hydrocarbon deposits, which are very common in things like oil fin processing. Nothing has really focused on ammonium chloride deposits that is involved in hydrogen recycled compressors. So our company took up the initiative to try to develop a coating and test it for something that would resist ammonium chlorides. We couldn't exactly simulate the operation of a compressor without having one in operation. So we attempted to determine how well a coating would resist how ammonium chlorides can deposit on the surface. So this test rig was developed where there is an ammonium chloride solution that is fed through a tube to a spray nozzle that is on an actuator arm, where every 30 seconds, this would spray a mist of a chloride solution on a coated panel. The coated panel was heated to just below 100 degrees Celsius to allow the solution to evaporate and help accelerate the deposition of chloride deposit on a coated sample. So we tested a number of samples to see how the coatings would perform in this environment. So a coating that was developed for this that we call PosiCode Protect. Performed very well in this test. I should mention that, I'm sorry, I forgot to mention this spray was applied every 30 seconds for a 24-hour period. And periodically in between the spray, a air blast was applied on to the coated sample, just in an attempt to blow the loose deposit off the coating sample, which gives a this was done in order to give a relative ranking for how well the propensity of a coating to release the ammonium chloride that was on the surface. So shown up top is a coating that worked, which we call PosiCode Protect, which did remove most of the ammonium chloride that deposited on the sample. Really, the air blast was focused on the middle of the sample, so that is really the only reason why it did not get the deposit that is shown at the edge. An example of a coating that did not perform, which is actually a coating that is used commonly in the industry, is shown on the bottom, where really none of the surface of the coated panel was clean, showing that the ammonium chloride deposits do build up on the surface. Even though this type of coating will release hydrocarbon fouling, it is not effective for releasing ammonium chloride deposits. Another factor in developing a coating is we looked at the durability of the coating, essentially by doing wear testing. For centrifugal compressors, they are expected to run for anywhere from 5 to 7 years in most applications without a shutdown. Hydrogen recycle compressors typically see 3 years or so, and certainly refineries would like to increase that time in between shutdowns. So looking at the wear test, we performed a Tabor abrasive test, which is really just you have a coated panel and you have a abrasive tip that the sample is rotated against, and you see how long it takes to wear through the coating sample, the coating. This is performed to a standard ASTM test, so this does provide a good relative ranking of the wear resistance of various coatings. As seen here on this graph, the PosiCode Protect far outperformed the wear, has better wear resistance than the industry standard coatings that are currently applied. While this is not a true fit for service test, this does show that it has higher durability than the coatings that are commonly used in the industry. A different type of wear test was a falling sand test. So this is a very highly scientific test where essentially you drop silicon carbide grit through a 1 meter long tube onto a coating sample, and you just measure the volume of silicon carbide grit that is needed to wear through the coating. Nothing real scientific about it, but it does give a very decent wear resistance of how a coating will perform in service, as solid ammonium carbide particles in this case will be impacting a surface that is rotating at a very high velocity. So the data is displayed in terms of liters of grit needed to wear through 1/1000th of an inch or 1 mil of a coating sample. It is very strange that the data is required to be reported in a mix of imperial and standard units. I don't know why it does that, but that is what it is asked to do. And you can see that the industry standard Teflon type coatings, they wear through relatively quickly. The PosiCode Protect in this case has a 10 times improvement over the industry standard coating. So again, this isn't a true fit for service test because every service will be different. However, it gives a good relative ranking of the wear resistance of the coating. We also performed corrosion testing, where ammonium chloride solution was placed into this tube where this utilized electrochemical impedance spectroscopy, which is the only method we could come up with to give a numerical value to the corrosion resistance of a coating. So what is measured during this testing is the capacitance behavior of a coating. Essentially, a good coating will act as a perfect barrier between the environment and the substrate that it is placed upon. That will effectively stop all corrosion. So what is shown here in this graph on the left is the impedance, the capacitance resistance over 2,000 hour time period. There's actually 7 or 8 lines all on top of each other here that showed that even from the initial start of the test through 2,000 hours, there was no change in the corrosion behavior of the sample. Essentially, the coating was remained intact after 2,000 hours. An example of a coating that did not work is shown here, where you could see at 0 hours, there's a good capacitance. However, over time, this capacitance downgraded as the coating was, the solution had diffused through the coating and caused corrosion. The industry standard coatings rely on a aluminum-filled chromate phosphate undercoat for the corrosion resistance, and this does work well in hydrocarbon fouling. For ammonium chlorides, the chlorides react readily with the aluminum, especially with the steel substrate behind it, and that leads to increased corrosion whenever the top coat is penetrated. The PosiCoat Protect does not rely on any sort of aluminum or undercoat to provide that corrosion resistance. Finally, we tested the bond strength of the coating just to ensure that there would be no issues with that. This is another standard test. Again, it's not incredibly complex. Essentially, a sample that looks like a chess pawn with the known surface area is glued to the substrate, and the force needed to pull that sample off is recorded. Now, this is a non-stick coating, so the gluing was a little bit difficult, so it does have to be etched a little bit to allow the glue to adhere. But the average bond strength was over 1 KSI, which is far more than what is required in order to remain adhered during service. So cross-section of the coating that is useful for hydrogen recycle service is shown here, whereas basically a permeation resistant intermediate layer along with the non-stick top layer is applied. This coating is utilized up to 260 degrees Celsius, which is normally well beyond the maximum temperature that hydrogen recycle coatings would see during service. And again, this was a coating specifically for ammonium chloride deposits, which again, the industry standard coatings have not really looked at that application. So the coating can be applied to assembled rotors, which is a significant benefit, especially for the service or spare rotors that are taken out during the turnaround. The rotor does not have to be, the impellers do not have to be unstacked from the rotor. The rotor, as a completed assembly, can have the coating applied. It is applied by a spray and heat cure process where the rotor is slowly turned during the entire process in order to avoid any sort of thermal bowing. It could also be applied to the stationary diaphragm components so that the entire flow path can be protected in hydrogen recycle compressors. So that is all for my presentation. I thank you for the opportunity to speak, and we will save questions for the end.
Thank you so much, Derrick, for that presentation. With that, we complete all the presentations for this session. We will now have the question answer session. I think most of the questions here are for Mr. Harwood and Mr. Bauer. So let me start with a lot of questions for hydrogen, right? So let me just start with the first question here. This is for green hydrogen presentation by Matthew. How the green hydrogen cost compares to gray hydrogen presently, and how do you see them in future? Matthew? Can somebody else on the panel take up this question, please, while we have Matthew join us? Derrick?
Unfortunately, I do not know the answer to that question. Sorry.
I think Mr. Bhandari would be able to
Yeah,
put some light on this.
So currently, I think green hydrogen is very, very costly as compared to gray or what is available from the refineries or reformers. But with the latest development which are taking place in the technologies related to electrolyzers, and also with the falling prices of renewable power, what is anticipated is that in next couple of years, maybe this cost will become comparable with the normal petroleum fuels like diesel and motor gasoline. So the hydrogen as a fuel has advantage that it has more energy per kilogram as compared to other fuels. So that will make it very, very interesting once it starts comparing with the normal fuel cost. And the electrolyzer technology is a very matured technology. Only problem is the cost, and with the demands growing, it is anticipated that cost also will come down significantly.
Okay. The next question is what special capabilities do fabricators need to build in to prepare for future hydrogen world? I think, Bhaskar sir, this question you'll be able to answer better. What special capabilities do fabricators need? What special capabilities do fabricators need to build in to prepare for the future of hydrogen world?
Ma'am, actually, I am not from that EPC side. People who are from engineering side or EPC side could have answered it properly, like Mr. But anyway, let me try to throw some light. Hydrogen plant do have very typical alloys put into it, and there are very specific skill set which is required for the fabrication of those. Those will, I think, will be applicable for hydrogen even with electrolysis, but it is unlikely to be as severe as we experience in that steam reforming process. So on a in principle basis, it will be more easier to fabricate with a electrolyzed hydrogen rather than a steam reformed hydrogen. Bhandari Sahab, I don't know whether I'm conceptually right. I think this will be the way it is. Secondly, I would like to go back to the first question, if I'm allowed. See, just to supplement. See, when you talk about hydrogen cost, gray hydrogen cost, you have to also bear in mind that almost all the refiners will in future go for net zero carbon. So that willy-nilly pushes us to something in the CCUS field. That means you have to capture that carbon dioxide that you will produce in the process of producing hydrogen. So to at least to go from gray to blue. So that itself is a cost. If you think that that is a cost, then your electrolyzed hydrogen will be more closer to a competitive cost of hydrogen. So this is what I thought I would share.
That is from an OEM side for centrifugal compressors, at least in hydrogen service. We follow API 617, and that does list a maximum yield strength. And I'm sorry, I don't have the megapascals value, but 120 KSI maximum yield strength is a limit applied to all metallic materials that are used in hydrogen service. So that is a general application that would have to be applied really to all equipment in high pressure service. And this is relatively easy to achieve, especially in terms of fabrication process, especially if a component is stress relieved. This does limit the highly stressed components like rotational equipment to some extent, and there are some Inconel alloys and some others that have shown a little bit of promise for exceeding that yield strength requirement in service, but in general, we're limited to a slightly modified yield strength for many hydrogen applications.
We have a couple of more questions.
Mavis, what I suggest that we can park the questions of Mr. Harwood and take questions of Mr. Bauer first. And in the meantime, somebody can contact.
I've been trying to message him actually.
Okay.
So this question, I think, what is the comparison between hydrogen and EV in transportation sector?
So probably what is meant by the question is that how the hydrogen will be used in the transportation.
In the transportation sector.
Actually, the two technologies are concurrently being developed and are in practice. One is the fuel cells, where hydrogen is stored in the fuel tanks in the vehicle, and then with the help of fuel cells, it is converted into power, which drives the vehicles. And second is the direct hydrogen injections into the engines. So both the technologies are maturing, and definitely if we use fuel cells, so it will not be as efficient as use of direct EVs, because overall conversions will be on the lower side. So the other technology, which is direct hydrogen injection, probably that will compare well with the EVs in future, with the falling cost of hydrogen.
So there's a lot of chat that is happening simultaneously, you know. So the question is, hydrogen production from azane. I hope I'm pronouncing it correct. NH3 azane. H2 production from azane prospect. How efficiently and economically can it be produced?
Yeah, I think it's quite an interesting question. So the hydrogen which will be generated from renewables, because ultimately what is being anticipated is that hydrogen will become a kind of a shield or a buffer to take care of the fluctuating natures of the renewable power. So when the power generation is excessive during certain seasons and time of the day, and there are no takers for that power, so that will be utilized for generation of hydrogen, which will be stored and later utilized for the lean periods. So now that hydrogen can also be stored as liquid hydrogen, which requires very low liquefaction temperatures. One also easy way to store hydrogen is convert it to ammonia by reacting with nitrogen. So which requires much lower temperatures to store. So probably, and then this ammonia can be utilized as a fuel, particularly for long haul transportations like ships and these vessels. So prospects are quite good because if we have hydrogen availability from the green sources, which is also cost competitive, then one of the competing technologies along with the hydrogen liquefaction into liquid hydrogen will be converting it to ammonia and then use ammonia as a fuel.
So I think the next question is also similar.
Would you like to add anything in this?
Yeah, I think you have answered it quite aptly. Few months back, there was a big news about blue ammonia being used in Japan. So that you can take it as a precursor. So ammonia has a great future if that these initial trials are successful. So this is what I wanted to add. Yeah.
So the next question is again related to transportation. They want to know what is the hydrogen cylinder pressure to be fitted in a vehicle, and what will be the cost per kilometer when using hydrogen as fuel?
Probably the current gas cylinder rules, they limit the storage pressure of populations so that the hydrogen had lesser volume of cylinders to store much larger quantities of hydrogen. So these things are still under proposal stage and under development stage. And finally, the cylinders which will be fitted into the vehicles, they will be comparable in size to current existing fuel tanks. And that will become possible when the regulations are modified to permit higher storage pressure of hydrogen in the vehicles. So these are still under development stage.
So the last question is, what are the developments in efficient storage of hydrogen?
I think this is what Mr. Harwood talked about, the liquefied hydrogen storage technology and their expertise in that. And Mr. Derrick also spoke about that. So probably these are the developments, latest developments which have happened. And the size of the hydrogen tanks, liquefied hydrogen tanks which are being built, the size is becoming bigger and bigger with the newer methods to fabricate them.
Derrick, would you like to add to that?
I can't speak all that well to it, but I do know that at least in the United States, the Department of Energy has asked for a certain pressure to be obtained through the hydrogen gas. And I believe that the purpose of that was for an optimized hydrogen storage capability. Basically storing hydrogen at atmospheric pressure just was not sufficiently efficient enough. They were looking for a specific pressure. I believe it was over 500 psi, maybe a little bit more than that. But I know that the pressure does play an influence on it, and they're looking for a specific pressure to aid in the storage of hydrogen.
Okay, we have one more last question. She wants to know, how far have we reached to implement hydrogen technology for commercialization in India?
Probably the electrolyzer technology in India is being used from 1960s onwards. We have ammonia plant in Nangal where the hydraulic power is being used to produce hydrogen. So these technologies are quite matured, particularly alkaline electrolyzer technology. But as I mentioned, the only problem is that they are quite costly technologies. And with all the concurrent developments which are taking place, like falling prices of renewable powers, the electrolyzers becoming cheaper. So with that, I think certain more maturity is required, not in terms of technological, but also to make it cost competitive. And with the recent thrust which is being given in the National Hydrogen Mission, which will come into effect from next fiscal, and also the fiscal support which has been given to develop these technologies, I think developments are going to be quite rapid. A lot of job is being done in various places on hydrogen as a fuel.
Okay, I can see that Matthew has joined us. This question is for you, Matthew. They want to know what is the largest size of green hydrogen plant implemented by McDermott?
Thank you very much. Well, at the moment, we are still looking at the hundreds of kilowatt scale. So, in terms of the actual projects in process, it's really the hundreds of kilowatts. But we're responding to more and more requests and concept studies and feed studies to look at multi megawatts and up to 100 megawatts. And you probably have seen in the newspapers some schemes even in the gigawatts. But practically speaking, the projects that we are actually currently delivering are still in the as I say, the hundreds of kilowatts of sort of level. But we expect that to increase very rapidly.
Okay, and there was one question which we could not completely answer earlier, and that was about what special capabilities do fabricators need to build in to prepare for future hydrogen world?
Well, I think from our point of view, there's some capabilities, I think, which are around metallurgy, which are very important because hydrogen, has a number of effects on metal, including hydrogen embrittlement, and so I think and certainly a knowledge of how hydrogen interacts with various metals is important. Health and safety, I think, is very important as well. This will be the new applications for hydrogen, and so you need to understand the health and safety concerns. And I think lastly, what I would say, particularly for an EPC company like ourselves, is really using the experience we have from large projects in refining and petrochemicals and oil and gas to really bring all of the components of a project together, including, for example, the electrolyzer, but with all of the balance of plant that you need in order to make the project work, storage, logistics. So really integrating the project and using the international supply chain to do that as well, so that we're doing, in the right activity in the right place geographically too. So yeah, there's a number of, I think, important capabilities that companies will need to add as they start to address this hydrogen opportunity.
With this, we end the session and the question answers as well. I would like to thank our moderator, Mr. Abhairaj Bhandari, and our panelist, Mr. Bhaskar Pukan, Mr. Matthew Harwood, Mr. Pramod Dalvi, and Mr. Derrick Bauer for joining us for this session.